Hello, and welcome back to our podcast, where we explore the fascinating intersection of mathematics and rocket science. Today we will be diving into the role of calculus in understanding the complexities of space travel. So buckle up and get ready for a journey through the cosmos, with calculus as our guide. Let's start at the beginning. What exactly is calculus, and how does one relate it to rocket science? Well, calculus is a branch of mathematics that deals with rates of change and accumulation of quantities. In rocket science, calculus is essential for understanding how objects move through space and the forces that act upon them.
One of the key concepts in calculus is derivatives, which represent rates of change. In rocket science, derivatives help us to calculate important parameters like acceleration, velocity, and position over time. Imagine a rocket launching into the sky by analyzing its velocity at different moments. We can determine how fast it's speeding up or slowing down. Crucial information for engineers designing rocket propulsion systems.
Derivatives, didn't we do those earlier this year in Miss Yanni's?
Yeah.
So Miss Yanni's basically teaching us how to be a rocket scientist?
Yeah, it's pretty cool.
Should have paid more attention. Derivatives can also come into play when optimizing rocket performance. Engineers will use calculus to determine the optimal thrust needed to project a rocket forward, ensuring efficient fuel consumption while achieving the desired trajectory. This involves maximizing the derivative of velocity, which is acceleration, and subject to constraints such as fuel limitations and payload requirements. We will put an equation up for this on the board. Now, since we've talked about derivatives, we can talk about integrals, which are the flip side of derivatives. Integrals represent the accumulation of quantities over time. In rocket science, integrals come into play when calculating fuel consumption. By integrating the rate of fuel consumption over the duration of the rocket's flight, we can determine the total amount of fuel expelled, a critical factor when planning a mission. This is like putting gas in your car and seeing how much you'll need to get from point A to point B.
So you're saying if I speed up, I'll use more fuel?
Pretty much, yeah. That's how it goes.
Integrals are used in rocket science to solve various problems related to motion, such as calculating the distance a rocket travels or how fast it's moving at a certain point in time. A way to understand this is, imagine you're driving a car and you want to know how far you've traveled. You could look at your speedometer to see how fast you're going at a given moment, but that doesn't tell you how far you've gone overall. To figure that out, you need to integrate your speed over time.
Calculus gives us the ability to enable us to model complex interactions between space and spacecraft, like the interactions between your road and your car, or roadcraft in this scenario. Differential equations, which are another branch of calculus, describe how gravitational forces affect the motions of objects in space. Whether it's plotting the trajectory of a satellite or planning a meetup with an orbiting space station, calculus provides us the mathematical framework for navigating the stars. In space, you have multiple different forces like gravity and a vacuum affecting your objects. So when you go up in space, you need to have a charted out route and for how to plan when you're up there.
Let's move on to another mathematical concept of orbital mechanics. Orbital mechanics are quite complex. I don't understand them that well.
I mean, to be fair, I don't really understand them either. We are not rocket scientists, at least yet, but hopefully in the future we have time to expand on that. But calculus enables us to model the complex interactions between space and spacecraft, kind of like the interactions between your car and the road.
Orbital mechanics are like the rules that govern how things move around in space, such as planets orbiting the sun or satellites circling the Earth. When we launch a rocket, we use these rules to figure out how to get it into the right orbit around the planet or into space. It's a bit like playing a game of pool or iMessage pool. where you have to aim the rocket just right to send it where you want it to go. By understanding orbital mechanics, we can plan rocket launchers to reach their destination and stay in orbit around planets and other objects in space.
So you're telling me all I have to do to win every single pool game I play is learn orbital mechanics?
Just a bit of math.
I think that seems doable. I think so. It's possible. I'll have to work on it. Now, calculus may seem really boring and only number crunching, but calculus actually has many real-world applications and is not only number crunching. It's about optimization as well. Consider trajectory optimization, where calculus helps us find the most efficient path for a rocket to travel. It does this by minimizing fuel consumption or maximizing payload delivery. Calculus allows us to chart a course that balances performance and efficiency essential for successful space missions. Basically, what trajectory optimization does is it allows us the easiest way for a rocket to travel from here to here while consuming the least amount of fuel in the safest path in between all the objects and debris up there in space. Trajectory optimization in rocket science is like finding the best path for a rocket to travel from its launch point to its destination. Imagine you're planning a road trip and you want to figure out the fastest or most fuel-efficient route to get to your destination. In rocket science, instead of roads, you're dealing with the vastness of space and space junk and maybe aliens and asteroids. There's a lot more moving pieces than on the road.
Lots of ice, too. Kind of cold.
Lots of ice, lots of satellites.
Definitely bring a jacket.
We got a lot of garbage up there.
Yeah.
Maybe we can use some calculus to plot the trajectory of getting it back to Earth. Who knows?
Throw it back in, burn it up.
Maybe we can become rocket scientists and solve that out.
Yeah.
I think this class is laying a lot of the needed foundations to us becoming rocket scientists. Today, in this episode, we talked a lot about rockets in space. Let's bring calculus down to Earth, or rather, where the magic happens and the work actually gets done. Real-world examples based off calculus in action during rocket launches and space missions. From the Apollo moon landings to the Mars rover missions, calculus has been instrumental in guiding spacecraft through the vastness of space with precision and accuracy. Without calculus, we would not be able to have any of the satellites, rockets, or space stations we have in space now.
Just simple equations.
I wouldn't call them simple, but speaking of equations, we will have the equations needed for this written on the board.
Moving on, as we look into the future, calculus will continue to play a pivotal role in advancing rocket technology, whether it's developing reusable rockets or plotting trajectories to distant planets. Calculus provides the foundation for innovation in space exploration. As we push the boundaries of human exploration, calculus will be our constant companion, guiding us on our journey to the stars.
Of course, no discussion about calculus and rocket science would be complete without acknowledging the challenges and limitations. Uncertainties are abundant in the area of space travel, from unpredictable weather patterns to unforeseen technical glitches. Yet through the lens of calculus, we can navigate these challenges with confidence, armed with tools to analyze, predict, and adapt to whatever space may throw our way. And with that, we have reached the end of our journey through the cosmos with calculus. From derivatives to integrals, from optimization to orbital mechanics, calculus shapes our understanding of space and propels us to new frontiers. So until next time, keep looking to the stars, and don't forget to bring your calculus brain with you along for the ride. Thank you. If there is any questions, please do not ask us about how to launch a rocket, because we are still figuring that part out. Thank you for watching.
Thank you.
And with that, this episode of our podcast comes to an end. We will now be leaving our rocket ship and ascend back to Earth. Thank you for listening.
Thank you.